and welcome to another NGen Math 6 lesson by eMath Instruction. My name is Kirk Weiler, and today we're going to be doing Unit 6, Lesson 3, solving one-step equations with multiplication and division. So in the last lesson, we saw how we could use subtraction and addition to solve equations in just one step. In other words, in order to isolate the variable. In this lesson, what we're going to be doing is we're going to be trying to use division and multiplication to solve equations as well. Let's get right into it by reviewing how we can tell whether or not a particular value of a variable is a solution to an equation. Let's do that in exercise number 1. Here we go. Big idea. Solving equations often comes down to performing the opposite operation to the one that has been done to the variable. All right, so in exercise 1, let's review a little bit about what we did in the last lesson. Exercise 1. Solve each of the following equations. All right, great. Well, again, there were tons of these on your homework from the last lesson, so what I'd like you to do is pause the video now, solve this equation for the value of x, solve this equation for the value of y, and then we'll move on to some multiplication and division. All right, keep in mind, right, when I look at this equation and I think about what I should do to isolate the variable, that means get the variable all by itself, I see that 8 has been added to x. So what I need to do is I need to get rid of that 8, right? It's kind of like saying, hey, I had some unknown amount of money, you gave me $8, and I ended up with $24. How much did I begin with? Well, to figure out how much I began with, you'd just take away the $8. Right? That's what you'd do. And it's the same idea here. If I've got this equation, x plus 8 is equal to 24, I'm going to simply subtract 8 from both sides. That positive 8 is going to be taken away by subtraction. Then 24 minus 8 is going to be 16. And there's my solution. Keeping in mind, of course, that if I made a mistake, let's say instead of subtracting 8 from both sides, I added 8. You know, I got like an answer, x equals 32. Then I could have easily put 32 into this equation and said, well, 32 plus 8, that's 40. 40 is not equal to 24, right? Remember, this value is only a solution to this equation if when you substitute it back in, it makes the equation true. All right, well, for letter B, of course, we've got the variable y minus 13 equals 21. Again, the same idea. Let's say I had some unknown amount of money, right? And I gave you $13, right? So $13 were taken away from the amount of money that I had, right? And then it left me with $21. If I really wanted to know how much money I started with, I would then add 13 to the 21, right? To get back to where I started. And the same idea is true here. If I have y minus 13 is equal to 21, I'm going to add 13 to both sides. That subtraction by 13 and addition by 13 just cancel each other out, and 21 plus 13 is 34. All right, so simple enough. We do the opposite operation to what has been done to the variable. If we've added to the variable, we subtract. If we've subtracted from the variable, we add. Now let's take a look at a little bit of multiplication and division. All right, exercise number 2. For each of the following equations, check to see if the value of the variable given is a solution to the equation. All right, well, we've done this quite a bit. So what I'd like you to do in both A and B is take the value of the variable that they supply us, x equals 6 and n equals 21, substitute it back into the two equations, and see if it makes the equation true. If so, it's a solution, and if it makes it false, it's not a solution. Pause the video now and go ahead and check this. All right, let's do it. So in the first equation, simple enough, I'm going to take my 6, I'm going to substitute it in for x, right? 3 times 6, does that equal 15? Well, 3 times 6 is equal to 18. 18 is not equal to 15, so I'm going to say false, and the answer then is no. It's not a solution. On the other hand, in letter B, if I take 21 and I substitute it into the equation for n, I'll get 21 divided by 7 equals 3, and 21 divided by 7 is 3. So since that is a true equation, the answer to this is yes. All right, so simple. Now, what this doesn't tell you is how I would take one of these two equations, this one involving multiplication, this one involving division, how I would take those two and in a single step figure out what the correct solution to the equation is. But now we'll get into that in the next exercise where we revisit the idea of an equation being like a balanced scale. Let's do it. Here we go. Exercise number 3. Consider the equation from exercise 2a, i.e. 3x equals 15. What is the solution to this equation? What do you need to do to both sides to have only one x? All right, so let's talk about this a little bit. Right now, forgetting about everything else, what we have is an equation that says 3 times some unknown number is equal to 15, right? I don't know what x is, but 3 times the number x is equal to 15. So all by itself, you should understand already, right, what the value of x is. Pause the video now and just write down what value of x you know will solve this equation. All right, well, hopefully you know that x equals 5 will solve this equation. And of course, the reason you should know that x equals 5 solves this equation is that 3 times 5 is equal to 15. Right, it's really as simple as that. But ultimately speaking, thinking back to this doing the opposite of what has been done, right? What has been done to the variable is that we've multiplied it by 3. In order to undo that multiplication by 3, we will do the opposite of multiplication, which is division. So what I will do in this situation, right, is I'll take my 3x equals 15, and I'll divide this side by 3, and I'll divide this side by 3. Now let's talk a little bit about this. A lot of times what you'll see from math teachers, very understandably, including me, is you'll see just like sort of a line canceling those out. But keep in mind what we really have here is we have 3 divided by 3, right? 3/3, or 3 divided by 3, would just be equal to 1, right? Now on this side, we have 15 divided by 3, and that's equal to 5. Now it's pretty rare that we actually want to write 1x equals 5, right? Just because it looks weird and that 1 could be confused with something else. So 1 times x equals 5, that's just x equals 5, right? That's exactly what we did. So we just needed to divide both sides of the equation by 3. Now, letter B says illustrate what is going on by using the diagram of the scale. All right, so, when we looked at the scale in the last lesson, and all we were doing was removing 3 blocks from both sides, that was pretty simple to illustrate. Here it's a little more complicated, but keep in mind that what 3 times x means is x plus x plus x, and then we've got 15, let's say, coins over here. Now, what does it mean to divide both sides by 3? Well, what it really means to divide both sides by 3 is to just kind of, all right, I'm dividing both of these things up, and what that means is that 1x must be equal to 5. I'm on 5. There it is. And then this 1x is equal to that 5, and this 1x is equal to that 5. But ultimately speaking, what we're doing is we're dividing this side up into 3 parts, dividing this side up into 3 equal parts, and we're saying, well, that 1 equal part, which is x, is equal to this 1 equal part, which is equal to 5. And that's it. And it really is that simple. If we look at an equation where the variable has been multiplied by a number, to isolate the variable, we're going to divide both sides by whatever that number is. So let's take a look at that and get some practice on it in the next set of exercises. Here we go. To undo multiplication of a variable by a number, divide both sides by that number. Exercise number 4. Solve each of the following equations. Show the work that leads to your answers. All right, this is really easy because I'm going to just rewrite it, right? We have something like 5x equals 45. I've multiplied x by 5, so what I want to do on both sides of this equation is divide by 5. 5 divided by 5 is equal to 1, and 45 divided by 5 is equal to 9. So my equation is x equals 9. And again, it's very easy to check. If I took the 9 and I substituted it back into this equation, I'd have 5 times 9 equals 45, 45 equals 45, and I would know that was a true equation, and therefore this is a solution to the equation. What I'd like you to do is now solve letter B and letter C the same way. All right, easy enough. Now, be careful about something. It's very easy at this point in algebra, because we're solving one-step equations, to just look at this and go, well, I know the answer is 3. I mean, 11 times 3 is 33, so the answer is 3. I can do it in my head. Same thing here, right? But eventually, you're going to be solving much more complicated equations that, trust me, you can't do in your head. And this serves as the basis of being able to solve those more challenging equations. So in fact, if I have 11n equals 33, and I divide this side by 11, and this side by 11, right? 33 divided by 11 is 3, and there's our answer. All right, letter C, same thing. We've got 6y is equal to 48. If I divide this side by 6 and divide this side by 6, notice how we're always using the fraction bar as division, right? 48 divided by 6 is 8, and that's our solution to that equation. All right, real easy. If the variable's been multiplied by a number, in order to get rid of that number, you're going to divide both sides of the equation by it. All right, let's take a look at a little bit of a modeling problem that involves this type of equation. Here we go. Oh, no, actually, we're going to do some messy division first. My apologies. Division can get messy, right? Multiplication tends to not be messy. Addition, subtraction tend not to be messy. But division can be messy, right? Because it can result in things like remainders and like ugly fractions and things like that. So let's just take a look at a little bit of that in exercise number 5. Solve each of the following equations. Write your answers as mixed numbers. All right, so I mean, again, in each one of those last cases, it was very, very simple to basically just go, all right, I'm going to divide both sides by 5 or 6 or whatever, and then the division turned out nice, right? Here's a great example where it might be kind of difficult to look at this and go, wow, what would I multiply 2 by to get 13? 2 times what is 13, right? So ultimately, it's actually maybe a little bit easier in this case to have this equation, divide both sides by 2, right? You then get n equals 13 halves. 2 goes into 13 6 times with a remainder of 1. So n must be 6.5. That's a little bit harder to just kind of work out in your head if you're looking at the equation, which is why it's good to know you just divide both sides. All right, so what I'd like you to do is do the same thing in letter B and letter C. Simplify your answers as much as possible. They'll both be mixed numbers like this. And see what you get. All right, let's do it. 6x equals 32. All right, so we're looking for what number we can multiply 6 by to get 32. We will do that by dividing both sides by 6. All right, 32 is not nicely divisible by 6, but 6 would go in there 5 times. That would give us 30, which would give us a remainder of 2, so it would be 5 and 2/6. That wouldn't be a horrible way of leaving our answer, but 2/6 can be reduced down to 1/3. So our answer in most simplified form is 5 and 1/3. All right, letter C, probably a little bit easier than letter B because there's less simplification. I have 3y is equal to 37. Divide this side by 3. Divide this side by 3. 37 divided by 3 would be equal to 12. That would get us up to 36. Then there'd be a remainder of 1. So y is 12 and 1/3. I like that 1/3 apparently. Anyhow, so yeah, division can be messy, right? And don't be surprised if you get kind of an ugly answer when you're solving these types of equations. You could easily get answers that are fractional. All right, now let's go on and do a modeling problem with this type of an equation. Here we go. Exercise number 6. Louise is shipping 8 boxes that all contain the same number of books. That's very important. She is shipping a total of 104 books. Let B equal the number of books in each box. Write an equation involving B and solve it to find out how many books are in each box. All right, let's find the relevant information here. This is very important. You know, she's got 8 boxes and they all contain the same number of books. We're going to let B equal the number of books in each box, right? So how many books are in each box? And we know that there's a total of 104 books. So all that stuff that I underlined and circled and whatnot is quite important. Now, if you knew how many books were in the box, if you knew that there were like 5 books in each box, and you wanted to know the total, you'd just do 8 times 5, and you'd get the total number of books, which would be 40 in that case, but whatever, right? We don't know the number of books in each box, but we could still say that if I took 8, I multiplied it by the number of books in each box, so 8 times B, right? That would have to give me the total number of books. I've got 8 boxes. B is the number of books in each box, so if I do that product, right, and whenever I have a number sitting right beside a variable, that's a product, that would have to equal 104. All right? So this equation then models what's going on in this problem. To figure out how many books are in each box is very simple. I then am going to divide both sides by 8. Right? That'll cancel. And maybe over on the side of your paper, you've got to do a little 104 divided by 8. You know, it goes in there one time, 8, subtract 24, then 3, 24, subtract 0. Oh, okay. So B must be 13. There are 13 books in each box. Now, if you said to yourself, wait a second, I remember doing a problem like this in 3rd grade, you know? I mean, if they tell me I have 104 books and they're being divided into 8 boxes, then I'm just going to do 104 divided by 8 to figure out how many are in each box. Absolutely. And again, what we want to do is we want to keep coming back to how algebra can help us visualize some of the things that we've already done in arithmetic up to this point in time. Now, so far, all we've seen are equations where we've got a variable multiplied by a number equals another number. Now let's go to the case where we have a variable divided by a number equals another number. Let's see how that works out. To undo division by a number, we multiply by that same number. Surprise! Again, you're always doing the opposite of what's been done. So let's take a look at exercise number 7. Determine the solutions to each equation below. All right, so let's talk about A a little bit, and then we'll kind of get at the general method. Look, at the end of the day, in A, we are looking for a number that when we divide it by 5 gives us 7. All right, you should be able to just sort of figure out what that number in your head is, right? It's 35. 35 divided by 5 is equal to 7. But how can we really get that without having to just kind of, let me think about this? Well, again, let me kind of rewrite the equation in sort of bigger form here. The idea is very simple. I have the variable, and it's been divided by 5, and that's equal to 7. If I want to undo the division by 5, what I'm going to do is I'm going to multiply by 5 on both sides of the equation. Literally there, you can think of this as cross-canceling when you multiply 2 fractions. You know how when you multiply 2 fractions, right? If there's something down here and something up here, you can cross them out. It's the same idea. I mean, literally, it's the same idea. I have x fifths times 5. Those 5s are going to cancel. I'm just going to be left with x. And then, of course, 7 times 5 is that 35. So we undo division of a variable by a number by multiplying both sides of the equation, absolutely critical, by that number. All right, let's do the last two together. All right, here we got n divided by 10 is equal to 2. I can then undo that division by 10. You don't have to put the 10 over the 1. I'm just kind of really hammering home the idea of that cross-cancellation. Right? And then 2 times 10 is 20. Now again, you know, as always, right, it's easy enough to look at A and B and just say, hey, in letter B, what number divided by 10 gives me 2? Well, that would be 20. 20 divided by 10 is 2. It's pretty obvious, right? But it's not nearly as obvious when you get into a situation like this, and yet it works the same way. I've got y divided by 4 is equal to 3 halves. It doesn't matter that it's equal to 3 halves. It doesn't matter that it's equal to 3 halves or 8 thirds or anything like that. The plain fact is, to get this y by itself, I need to multiply both sides of the equation by 4. That's what I have to do. So when I come over here, right, what I'll do is I'll multiply this side of the equation by 4 and this side of the equation by 4. That will isolate the y. And then I just have to know how to multiply a whole number by a fraction, right? And that gives me y equals 6. Right? And that would have been a little bit harder. Oh, well, what should I divide 4, or what number divided by 4 gives me 3 halves? It's a little bit harder to think about, right? At least a little bit harder to think about than A and B. Let's do one applied problem where we kind of use this setup, and then we'll wrap up the lesson. Here we go, exercise number 8. Jalen is dividing his playing cards into 6 piles. Each pile contains 7 cards. Let C represent the total number of cards that Jalen has. Write an equation involving C and then solve it to find out how many total cards Jalen has. Okay, so let's take a look at this for a second. Right? Jalen divides his cards into 6 piles. Each pile contains 7 cards. Right? C represents the total number of cards. Okay, now this really is a little silly to set up an equation in order to solve this, but here's how we think about it, right? If I took the total number of cards, however many it was, and I divided them up into 6 piles, I would show that division as following, right? I'd take the total number and I'd divide by 6, all right? And that would tell me how many cards are in each pile, right? But we're told that each pile contains 7 cards. So I'd have to get this. The total number of cards divided by 6 equals 7. In order to solve this equation, right, I can now multiply both sides by 6. That division and multiplication by 6 cancel, and 7 times 6 is 42. And again, if you're thinking to yourself, boy, I really don't need algebra to do that, absolutely. If I've got 6 piles and there are 7 cards in each pile and I want to know how many cards there are, I'm going to do 6 times 7. I'm going to get 42, right? But again, what we're looking at here is how to model this scenario using an algebraic equation and then how to use those opposite or inverse operations to isolate the variable and get the solution to the equation. All right, let's wrap this all up. So today we actually saw something that wasn't that different than what we've seen already, which is that if we look at an equation where the variable has been multiplied by a number or divided by a number, then we can isolate the variable by literally doing the opposite of what's been done to it on both sides. So if I've multiplied the variable by some number, I'm going to divide by that number on both sides. If I've divided the variable by some number, I'm going to multiply by that number on both sides, right? So it's actually quite easy in that sense, in that it follows exactly the same pattern as what we saw with the addition and the subtraction. Now in the next lesson, we're going to use all of this with some equations that get rather messy with fractions and decimals, but that's okay because we've got the basics already down. For now, I just want to thank you for joining me for another NGen Math 6 lesson by eMath Instruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.